Hello everyone. So let's now solve question number 3. Which of the following options are true? Option 1. So the number of linearly independent vectors in a vector space can be more than the dimension of vector space. So from the definition of dimension of vector space, we know that the number of linearly independent vectors in a vector space V can be at most dimension of vector space V. While option 1 tells they can be more than the dimension of vector space. That is wrong statement, hence option 1 is incorrect. Now let's look at option 2. The dimension of vector space spanned by these vectors is 2. So consider the set S. So if we put down these matrices, -1, -1, -1, 1, 1. So we need to find the spanning set, dimension of the spanning set of these matrices. For that, first we can try checking whether these vectors or the matrices are linearly independent or not. So to check whether these are linearly independent, we can form the linear combination of these matrices plus beta time plus gamma time, and we can equate it to a zero matrix. Just how in the case when we have vector, we equate it to a zero vector. Here we will equate it to a zero matrix. So if we simplify this, we will get gamma alpha minus beta plus gamma alpha plus beta plus gamma. So we will get the system of linear equation as alpha minus beta minus gamma equal to 0, minus alpha plus beta plus gamma equal to 0, alpha minus beta plus gamma equal to 0, alpha plus beta plus gamma equal to 0. Consider this is equation 1, 2, 3, 4. Now, if we subtract or if we add these two equations, that is equation 2 and equation 3, so on adding equation 2 and 3, uh, these two will cancel out, so we will get gamma equal to 0. Now we can put gamma equal to 0 in equation 3 and 4, so we will get alpha minus beta equal to 0, alpha plus beta equal to 0. Now adding these two equations, we will get alpha equal to 0 and beta equal to 0. So we get all three coefficients as our 0, and we know from the definition of linear independence that if we are able to get all the three coefficients or when we try to form the linear combination as 0, if all the coefficients are 0, that means the vectors in that set are linearly independent, and if any one of them is non-zero, then they are not. Now, as they are linearly independent, that means the dimension of the set spanned by these matrices would be 3, while in option 2 itself it is 2, hence option 2 is wrong. Now let's look at option 3. dimension of vector space spanned by the vectors is 1. Now consider this as set S2. So these are the matrices that are given in the option 3. Now we need to find the spanning set of these set. So if we try and observe, we can check that this matrix is the negative times of this matrix. So let's consider this as matrix 1, M2, M3. Then M2 is equal to negative 1 times M1, and M3 is negative 2 times M1. So that means for the spanning set, we only need one of these matrices. Either we can take this or this or this. We need only one matrix to span this entire set. So the spanning set for S3 would be just this. We could have chosen this matrix also or this matrix also. It doesn't matter. The spanning set formed by the one of these matrices would be the same. And as there's only one vector in this set, so the dimension of that spanning set of S3 would be 1. And option 3 also says it is 1. So option 3 is correct. Now option 4, the number of spanning vectors can be more than the dimension of vector space. So this also comes from the definition or properties of a spanning set. So let S is a spanning set for some vector space V. Okay. Then S must contain at least dimension of V vectors. So in other words, we say that the dimension of a vector space is equivalent to the number of elements in its basis, and basis is a minimal spanning set or maximal linearly independent set. So if we are claiming that one set to be a spanning set for a vector space, then it must contain at least the number of dimension V vectors. Or we also know one more fact that superset of a spanning set is also a spanning set for the same vector space. Okay. So any superset of a spanning set is also a spanning set for the same vector space. So this means that option 4 which tells that the number of spanning vectors can be more than the dimension of vector space. That is true. So let's now solve practice assignment week 4, question number 7. Find out the value of A for which the matrix will be in the spanning set of matrices, this and this, with usual matrix addition and scalar multiplication. So first let's name these matrices A, and then we have, let's say, set S, which consider this matrix and this matrix. So If matrix A lies in the spanning set of the set S, that means there exists some alpha and beta such that alpha times this matrix plus beta times this matrix is equal to our A. So for some alpha and beta, if we take the linear combination of alpha and beta with these matrices, then we will be able to get this matrix as our matrix A belong to the spanning set for the set S. So if we simplify it, we will get alpha beta 0 minus alpha equal to A 1 0 minus 1. So on comparing, alpha equal to A, beta equal to 1. So this 0 equal to 0 and minus alpha equal to minus 1. So that is alpha equal to 1. And as alpha equal to A also, so we get A equal to 1. So that is our answer. Thank you.